imaging. So in the book's very good on this stuff. So the chapters 3 and 4, 3 for the image quality stuff, you should read that and pay attention to it. And most of the figures are going to come out of that. And chapter 4 is good as well. And so recall we were looking at what an image is, and it's a spatial, modulation of a signal, right? So if you have just a plain gray background, that's one image, but there's nothing in it, right? It's like the null image. And then structure gets built up in an image, and by changing the intensity as a function of position in the field of view. And fundamentally, you can create any function in that field of view using Fourier expansion or Fourier coefficients. And so a lot of what we're going to do in this course is looking at the spatial frequency spectrum of images, like what edges have very high frequencies, sort of smooth Gaussian functions have lower frequencies, etc. And so the understanding of what a modulation is in an image is on this slide here, where we have a constant background, and then we modulate the intensity as a function of position in space with a sine wave. That's the simplest kind of modulation we can do, right, other than just a constant line or something like that. And if we're going to build up a set of pictures from Fourier expansion, then all of these spatial frequencies would be in the function that we're trying to image. The reason it's very convenient to look at it that way is because most of the time the description of how your imaging system modifies the spatial frequencies that are on the input side of the system to the image that comes on the output side, that is usually described as a linear system where frequencies come in, they get attenuated a certain amount, and they come out the back end of your detector, right? And that's described here. This is out of the book again, where you have some kind of modulation comes in, your imaging system attenuates that particular spatial frequency, and that's what comes out the back end. And that's essentially a filter, right? So if I have really high frequency noise and I put that one-dimensional amplitude signal through a filter such that it gets, only the low frequencies come in, all of the clicking and clacking goes away, the high frequency stuff. Similar with images, where the high frequency stuff are spikes in the image, that's really high frequency data, or really sharp edges that are high frequency data. So this is usually described as a modulation transfer function that describes the behavior of the whole imaging system. So here's an example of a bar pattern, and this laser here, where we have essentially a spatial frequency, or cycles per millimeter in the plane, right, of a bar pattern, and that spatial frequency increases as I go farther down the pattern here, such that I have more cycles per millimeter here than I do up here, right, or cycles per centimeter, whatever you want, it's in space along this direction. And if my imaging system attenuates low frequencies very little, say 90% of this signal goes through my imaging system, what the output looks like, is this. Right? It's the edges of this thing are blurred, but you can see this fundamental frequency is still there. You're still going to have maximum contrast between the trough here and this peak here, right? As we go to higher frequencies, the system may attenuate those high frequencies. So here we have a much higher frequency, 4 cycles per millimeter, and the system may attenuate that by as much as 90% or close to 90%, 87%, such that frequency, when you look at it on the output, there's a point at which you can't even determine that there is an oscillation there anymore. It's just crushed down into a mean value. Okay? And that's what's called the modulation transfer function. It's how these spatial frequencies are passed through the system. You can graph this attenuation as a function of spatial frequency. And we'll say at very low frequencies, 100% of the signal comes through. As the oscillations get higher in frequency, here's 3 cycles per millimeter, 4 cycles per millimeter. This shows you how much it's attenuated. This function is called the modulation transfer function. And once you've measured that for your imaging system, that characterizes the effect that your system has on the spatial resolution of the signal coming in. You know, all of us have modulation transfer functions in our eyes, right? You can see up to a certain spatial frequency with your eyes, and some people need glasses to see, you know, high sharp edges, right? And so there's kind of that limit. There's no point in making pictures that are far beyond that limit for someone who's observing it as to whether or not they can see the higher frequencies. You kind of get to this point. If you go to Circuit City or wherever the hell they sell TVs now, you know, and you see the highest resolution television you can get, it's getting to the point where it's kind of beyond your perception, right? That if you stand at 3 meters from the TV and the actual spatial frequencies that are coming out of that thing are probably higher than you can actually perceive with your eyes, right? So that's the modulation transfer function. And here's just some very simple examples of how the MTF changes the appearance of images as it changes. Okay, so here's an image acquired with a CT scanner, and the parameters for the acquisition of this will make sense to you in a little while. This is the tube current, the amount of electrons hitting the target. This is the energy of those electrons, the peak energy, and it produces this picture, right? If we crank up the tube current, right, to a higher value and the energy of those electrons, we get a better picture, right? So the raw data that is used to make this reconstruction just has better high-frequency information in it than the data for this one. Because when we zoom in and look at, you know, these line pairs here, these are holes drilled in the phantom. You can see an oscillation in intensity. Where the hole is, you get a dark signal, and where the background is, you get a bright signal. In that first image, when we do that same profile, we get something that looks like this. And so that modulation has gone down at this frequency. If we did the same profile up here at the low frequency, we would see basically no change, except at the edges of these holes, right? The edges would be blurred, but the depth of the hole would be the same. So any questions about that? Okay. We talked about this last time, that we have another way of characterizing the spatial resolution is to put a very small object, let's say the size of the laser pointer here, a little dot, and we image that dot. So that's the only thing in the field of view is just in X-ray you could use a gold bead. Sometimes what we use is we take a pen, like a cheap ballpoint pen, and you just take the ballpoint out of the pen, and that gives you a really hard little metallic sphere. And you image that, and it's well below the basic pixel size of the picture you're going to make. And then when you image that thing, what you get is a Gaussian function. It's a blurred picture of that dot that is quite tiny. You can't resolve that thing in your imaging system. That's the point. We're using a impulse signal that's much higher spatial frequency than we can resolve, but you can measure the shape of this curve. And that gives you the sort of underlying point spread function of a delta function or a very small dot in your imaging system. And you can imagine that if this width gets wider and wider for different systems, that means if it's wider, that's a lower resolution system, right? It blurs that signal into a broader spatial distribution. If it's really sharp and narrow, then it's a high resolution system. Okay. The Raleigh criterion is developed by taking two of these dots and bringing them close together and asking the question, when can you no longer perceive that you have two dots and you just have one signal? And that's another definition of spatial resolution. Interestingly, super resolution microscopy is done by having events that you detect at a low enough frequency such that this overlap here doesn't ever occur, right? And so you get sort of individual events detected in your microscope. Each one is one of these point spread functions, but if it happens in isolation, you can actually measure where is the peak of this thing, and that's where my object is. And so you get around this resolution limit by just reducing the flux of signals such that you get these independent Gaussian blobs coming out, and you map basically the center of mass of each of those blobs, and that gives you a quote-unquote super resolution image, right? That's in a different course, though. This is what's defined in the book as local contrast. So if I have in space a signal, and I have say a background, and then I have a target object here, and then a background again, a definition of local contrast, according to the book, and we'll use this definition for local contrast, is the difference in signal intensity measured between the background and the target divided by the signal in the background. So that's essentially like a fractional change or a percentage change in signal, right? Gives you your contrast. This definition of contrast makes sense for X-rays if you're counting X-rays. It also makes sense if you're counting nuclear decay. So you have basically a radionuclide in the patient and it's giving off gamma rays and you're counting those. Then this contrast makes sense. And the reason it makes sense is because regardless of the total number of photons that we detect in our detector, this fractional contrast will stay the same, right? As we detect more in the background number increases, as does the target number, and this fraction will stay the same. Just your ability to measure the accuracy of that will increase as you use more photons. Right? However, people don't really perceive this, right? This is a good definition for X-rays. If you're doing plain film X-ray or you're looking at raw data for CT, what humans perceive when you're looking at an image is essentially just the raw contrast to noise between the object, the background, and how much noise is in the field of view. And we'll see that definition in a minute. And most of the assignments we do and everything will use raw contrast to noise as opposed to this fractional local contrast as it's defined in the book. So here's just an example. That's the same phantom. Well, actually, we'll return and look at this part of the field of view to look at the signal to noise or the raw contrast to noise between this dot and the background, but that's going to come a bit later once we introduce noise. So noise is essentially random signal that's superimposed on your object. Okay? And the difference, so sometimes you will see just an increase in the sort of random signal. Just you can't really use television noise anymore because television noise is all busted up, bad digital transmission. But I don't know if anybody listens to a radio anymore, like in the car. But sometimes when you're going between stations, basically all you hear is noise, and that's just like white random noise. That's voltage that just has no pattern, right? It's an interesting concept. It's just like if I have a string of numbers and they're truly random, right? That's called white noise. That means all frequencies are represented in there. High frequencies, low frequencies, everything. equally well. And so if we look at this picture on the right, there's a lot of noise in this picture. There's just random pixel variation on top of our underlying signal, right? So you can quantify that just by looking at the statistics of that random signal. This is distinct from artifact, which is signal that isn't the object, right? But is itself somehow coherent, right? So you might have a reflection of the object superimposed on the object or something like that. That's artifact. That gets in the way of your perception of the object, but we usually don't characterize that as noise. Noise is a random signal. The signal-to-noise ratio is usually computed by taking a mean value in an area and then sampling some place where you can sample the noise to figure out what its amplitude is, right? And then calculating a ratio. So if we look at this set, which was on the last slide, the signal-to-noise ratio is going down significantly as we go here because the mean value of the brain here divided by the amount of noise is going to be a smaller number than over here. As we blur the image, or we can pass, say, a convolution filter across the image, or we can blur it with averaging, say, 4 pixels in a group together and move that across the image. You will increase the signal to noise, but you'll reduce your spatial resolution as you blur. So here's an example of a phantom that we use to look at the CT scanner that we work with. And this phantom represents a heart. And the gray stuff here is a resin that comes out of a 3D printer. And this is a cavity. And in the cavity, we put contrast agent. And so you get brightness here, resin here. This is air back here, right? This acquisition, everything, so that we set energy, etc., and we crank up the number of electrons hitting our tube to make X-rays to 600 milliamps, right? Is the current. And the reason we pick 600 is that as high as you can go. That's as much as you can do. You can crank away, it's not going to give you any more, right? 50 MA is as low as you can put that current. And I'm not really sure of the confidence of when you ask for 50, might give you 47, might give you 43, I don't know, it might get a little bit imprecise down there. But fewer electrons are used to make X-rays. We have fewer photons to make this picture. And you can see the difference in the signal to noise, right? There's a higher amount of noise in the background here than there is here, okay? When you look at your, this is the new, should be in the new slides. This region of interest can be drawn around a group of pixels, and inside that region of interest, you can calculate the mean value of the image intensity there, and in this case, it's like 673 is the mean value there. The units don't matter right now. The standard deviation of the pixels inside that circle is 29. So the mean is 672 divided by 29. So that kind of gives you the confidence you have in that mean, in that area, or the probability of getting a pixel of a certain value inside this stuff. It should be uniform, right? Right here. When we use 12 times as many photons to make the picture, we get 675, so it's basically the same mean. And the standard deviation here is 10. So it's dropped. We get a much more constant value. And you can take a look at the different values on the slide itself. So what does it mean to characterize the noise in the background? So let's put a box around this area of that phantom, the first phantom we looked at, and we'll just plot as a histogram the pixel values inside that box. Right? So I have you know, it says I have 20,000. I don't believe that. Pixels inside this box, and that's the distribution of values I see. Okay, so it's around a mean here of 195 right here, plus or minus we assume this is a Gaussian distribution, a normal distribution, with a sigma value of 3.4. And so the sigma value tells you the spread of random values in that background. In this image, where we use fewer photons, we use the same scale. When we plot the histogram, we get something that looks like this. It's much broader, right? So the mean is 192, basically the same, but now sigma, the distribution, the width of that is 8.3, and so the noise is higher, right? So this is that single number, 8.3 in this case, 3.4 in this case, basically characterizes the level of noise in that field of view, under the assumption that that noise is following a Gaussian distribution, usually. Right? Sometimes, and most of the time for the imaging stuff we do, it will be following a Gaussian distribution. It'll be a normal distribution of random numbers. Right? And so now, let's define the contrast to noise ratio, the local contrast to noise ratio. This isn't that definition we were looking at previously of local contrast. This is the contrast to noise ratio between this target signal and the background. We measured on the previous slide the background RMS was root mean square deviation, RMS or sigma, is 3.4. And so we look at the signal of the object, we do a profile through the object, and we see here's the background, there's the object. It goes down to 115 here and comes back up to 195 here. So it's 115 minus 195 divided by sigma. So that's the signal to noise. Signal to noise for this object right here is 23.5, minus 23.5 because it's negative, right? Here, we do the same thing, draw a line through the object, measure what the minimum value is right here. It turns out to be minus 156. So now we have 156 minus 192, which is the background mean, divided by 8.3. So the signal to noise of this object here in the background is minus 4.3. Minus 23.5 minus 4.3. Those numbers are important. And the reason is you can characterize the ability to perceive things with these numbers. So if I ask you the question, is there an object in this field of view? The probability you would get that right is proportional to this signal to noise, right? And so here's this dot. You have to decide, is that real or is that just noise? And it turns out that if the signal to noise is 5 or greater, you're going to be correct 99% of the time. If the signal to noise gets down to about 2, you're wrong maybe 40% of the time, right? So, and this is essentially when you get to understand images and you look at a picture and you say, well, what's the signal to noise of this picture? This is the parameter that people mostly use, yeah.
So you're using a phantom to do this sort of diagnostic understanding of how your system operates. Does that have to be done with different types of tissue, like with a phantom that mimics different types of tissue, different types of based on the environment and the organ that you're looking at, or?
Right. So I'm going to repeat the question because I don't think this mic will pick it up. So the question is, which that's fine. The question is, if you're characterizing the ability of your system to produce a specific signal to noise, do you have to do it with particular materials and particular patterns? And the answer is yes, right? So, and the reason is, specifically in X-ray, as we'll see, different materials attenuate X-rays differently, and they also modify the energy spectrum of the beam differently. And so where an object is in the field of view actually matters, right, for these parameters. So it's pretty complicated in CT and X-ray. In NMR, it's less complicated. Right? Okay, so that takes us to the end of image quality, and now we're going to look at X-ray imaging and X-ray production. No, that's 17. I think this must be it. Yeah, okay. Okay, any other questions about base? Yes?
I don't know if you were using signal noise and contrast noise interchangeably. Are they the same thing or different?
Could you repeat the question?
Are signal to noise and contrast to noise the same thing?
Actually, not really. So contrast to noise is what you use when you have a background and a target in the background. And signal to noise is what you measure when you just put an ROI on a part of the picture, measure its amplitude divided by the noise. So if we go back to the picture we had up here a second ago, let's go back to here, okay? So if I measure the signal intensity inside this region of interest and then divide it by the noise, that is the signal to noise of that material at that position, okay? If, on the other hand, I measure the signal difference between this, and I assume the noise is the same over that field of view, then the contrast to noise would be that signal difference divided by the noise. It gets a little complicated because in X-ray imaging, the noise, as you'll see when you look at these values in your slides, the noise here is actually different than the noise here. And so now you have to pick, okay, let's take maybe the average of the noise or some other definition like that, or maybe the larger of the two noises. It turns out that when you have high intensity pixels in CT, that means the attenuation of the photons was greater. And we'll see why this is true. So this is a contrast agent which attenuates more photons. That means that the detector saw fewer photons in making this picture than it did in making this or air, right? And when you have fewer photons, the uncertainty in the number you count goes up. And so the noise changes depending on the value of the thing. So that was a good question. So signal to noise is just an element itself divided by its noise. Contrast to noise, you look at a target and a background.
So I have one question.
Yeah.
So, with regards to the value and to determine if what you're looking at is actually a noise or actually another object in the background, you said that the numbers, but that only comes with contrast noise because you're learning the difference between what you know is
Correct.
your object. But if you don't, for example, if you didn't know, like,
Yeah.
because sometimes when you're imaging, like, you're not sure if
What am I looking for?
What you're looking in the object region per se
Yeah.
is really not noise. Like in that case, like, does the value like make a difference to help understand that? Or
Absolutely. So I think, let me rephrase the question
Yes.
or paraphrase the question. So the question is if I'm trying to perceive an object in the background, and what I told you was this, it's called the Rose criterion. If your contrast to noise is greater than 5 and it's like a disk in a background, then you have a 99% chance of correctly detecting that object is there. What's your performance when you, one, don't know what the object looks like,
right.
and if it's there? And that dramatically affects your ability to detect it. So if you have a large field of view and you're saying, you need to now find an object in this field of view, and you have no idea what its shape is, then your performance is going to drop, right?
So it's just for in case you do.
Right.
Okay, gotcha.
Obviously, if the object is bigger, sometimes it's easier to detect because you can sort of get a mean value over the whole field of the object. And if the mean value of that object is slightly higher than the background, you'll be able to perceive it because you can average more pixels in your head, right, or in your brain.
I guess my only follow-up to that is with regards to noise. Then defining
Yes.
noise, is it easy to define that in terms of it always being uniform, like a Gaussian pattern, like you said, or because in case there's like a significant like blot,
Yeah.
then you know in only one area, and the remaining part around that is not insignificant, but there is like noise in it. Noise. It's like
Most of the time, we're going to model the noise as being a uniform, random, white process around the object we're trying to detect. Okay. And anything else we model as artifact, right? So if there's a streak or there's some kind of other unwanted signal in there, right?
Thank you.
Sure.